So hello everyone. In this video, I wanted to make some two examples related to the idea of complex power. Okay, in particular, I will first try to solve the following circuit in which we need to compute first the power factor of the circuit. Also, we want to compute what is the what is the uh, power consumed uh, by the load. And three, we want to compute what is the what is the capacitor? Okay, what is the capacitor that you need to connect in order to improve the power factor to 1. Okay, so these are the 3 points. Now we want to compute the power factor of the circuit. Then we need to compute the power consumed by the load. And also the capacitor that you need to connect in parallel, no? Remember that in order to improve the power factor, we need to connect a capacitor in parallel in order to improve the power factor, okay? So, this is a very simple circuit, no? In fact, we can say that the current is flowing in this direction, and we can compute the current first in order to compute the complex power, because remember that the complex power is equal to the RMS voltage phasor multiplied by the RMS current phasor, but we need to take into account the conjugate. And this is equal to the RMS voltage times the RMS current, okay? And the angle of this is the phase angle of the voltage minus the phase angle of the current. Okay, here if you have the complex number in polar form, like in the case of the current, and you want to compute the conjugate, you can compute the conjugate by considering the negative sign of the angle. Okay, so you only need to change the sign here from positive to negative to compute the conjugate. Okay, that is why we have this phase angle difference, no? Between the phase angle of the voltage and the phase angle of the current. So this is the phase angle difference, and the complex power can be also expressed in rectangular form, no? Where we have a real part and we have an imaginary part. Okay, so the real part is the average power. Okay, this is the average power. Okay, and these are watts, and this is the reactive power, no? And these are bars. Okay, this is the unit volt ampere reactive, and the average power is the R watts. Also, this value, okay, the multiplication between the RMS voltage and the RMS current is the apparent power. Okay, so this is the average power, this is the reactive power, and this is the apparent power that has units of volt ampere. Okay, and what else? Well, this is like the complex power. Also remember that the complex power can be plotted in the imaginary plane. Okay. So if we plot this complex power in the imaginary plane, you will have here one complex power, no? If the reactive power is positive, no, that means that you're in the first quadrant. Also, that means that you have a inductive load, okay? and that the power factor, no, if the complex power is in the first quadrant, that means that the power factor is lagging, okay? If you're in the fourth quadrant, okay, that means that you have a capacitive load, and that means that that you have a power factor that is leading, okay? So basically, this is related. Now, if you're in the first or the fourth quadrant, that means that you have um, positive reactive power or a negative reactive power, and the real part is plotted in the horizontal axis. Okay. So according to these definitions, we can compute the power. We need to compute the power factor. Also remember that the power factor is equal to the cosine of the phase angle difference between the voltage and the current. Okay, so we can take this angle difference, no, or the angle resultant from multiplying these two values, and you can compute the power factor. And with this power factor, we can well, we can solve this first problem. Okay. So the idea is as follows. We can apply the Kirchhoff voltage law to this circuit. So in this case, you will have minus 120 with an angle of 0 degrees, volts RMS, plus I. In this case, I want to compute the voltage drop in this impedance. So you have 10 plus 12J ohms, and this is equal to 0. Okay, and if we solve this equation for I, you will obtain the following. And you will get a value of 7.6822 with an angle of minus 50.1944 degrees amperes RMS. Okay, this is the current. And what else? Well, we now have the current. In fact, this is an RMS current because we have an RMS voltage. So we can apply this definition of the complex power as S is equal to the RMS voltage, okay, multiplied by the conjugate of the RMS current. Okay, and you need to consider the conjugate. Basically, you only need to change the sign of the angle. So we can do that. We have 120 with an angle of 0 degrees volts RMS multiplied by 7.6822 with an angle of 50.1944 degrees. And this is equal to and 922.5865 with an angle of 50.19 44 degrees, and these are volt ampere, okay? And this is the apparent power. Now, we need, well, as you remember, we need to compute this power factor, okay? But before that, I want to express this complex power in rectangular form. So if you express this polar number in rectangular form, you will obtain the following. You will notice that we have 590.19 19, sorry, it's not 19, sorry for that, it is 16, okay, plus 708.19 J volt ampere, okay? So remember that when you express the complex power in rectangular form, you will have the real part and the imaginary part. The real part is the average power, no? Is the power that is being consumed. And the reactive power is Q, no? No, this is the reactive power, no? The imaginary part of the complex power, okay? And also, well, if we take the angle of the complex power, no? Remember that the power factor is equal to the cosine of the phase angle difference between the voltage and the current. But we know that this phase angle difference is the angle of the complex power, that in this case is the cosine of 50.1944 degrees. Okay, so this is if we compute the cosine of this angle, you will notice that the power factor is equal to 0.64, 0.18, and well, we can also plot this complex power in the imaginary plane. So we know that well, we have here the real part, no? This is P, and also Q is positive, okay? The reactive power is positive. So that means that the complex power is in the first quadrant. So based on this data, we can say that the power factor is lagging, okay? Because the complex power is in the first quadrant. So the power factor is this value, 0.64, and it is lagging because the complex power is in the first quadrant, okay? Because the reactive power is positive. Okay. And what else? Well, now, if you notice, we have tackled the first 2 points. We have computing the power factor and also the power consumed by the load, okay? But remember that the power that is consumed is the average power, okay? That is the power that is being consumed by the load, okay? The reactive power is only the power that is being stored by the inductor here, no? Or the inductor connected here. And for point number C, that is, we need to correct the power factor. In this case, we want to improve this power factor of 0.64 and improve that power factor to 1 or to unity. So to do that, well, we know that the new power factor, no? The new power factor is 1. Okay. So the idea is that we want to move the original the complex power, the first complex power, I want to move this complex power from this position and move it to this position. No, well, in this case, since the power factor is unity, I want to move it to this position, okay? So here we have the first angle, no, for the first complex power. But in this case, since the power factor or the new power factor needs to be 1, you know that the power factor is equal to the cosine of an angle, no? In this case, what is the angle that provides, well, what is the angle that provides a value equal to 1, no? The cosine of the angle that is equal to 1. Well, we can solve this equation to compute the second angle, okay? That is the inverse cosine of 1, okay? And that is equal to 0, okay? So the second angle, no, or the angle associated with the new power factor is 0 degrees, okay? So that is why I'm saying that I need to move the complex power from this position to this position. Now we have a formula to compute what is the reactive power that the capacitor needs to provide to the circuit, okay? What is the reactive power that this capacitor needs to provide to the circuit in order to reduce the reactive power to 0? Because we are basically doing that, no? We are moving the reactive power from this value and move it and reduce the reactive power to 0. Okay. So the formula that you can use to compute that reactive power that the capacitor needs to deliver is the real power of the circuit times the tangent of the first angle minus the tangent of the second angle, okay? So we know that the second angle is 0, so the tangent of 0 degrees is 0. So we can say that the reactive power of this capacitor should be equal to the real power, that we have that real power, no, is, or this average power, that is 590.16 times the tangent of the first angle. But we know that the first angle is 50.19, okay? 50.19, 44 degrees. So the reactive power is equal to 700.19 volt ampere reactive, okay? In fact, you can see that this value is equivalent to the reactive power that we originally have, because we want to connect a capacitor that provides the same reactive power, no, that we have in the original circuit. The only difference is that we want to cancel, no, this original reactive power with the reactive power of the capacitor. Now, the value of the capacitor that will provide this reactive power is QC, no, the reactive power of the capacitor, divided by the frequency times the square voltage. Okay, so the reactive power of the capacitor is, well, the capacitor value is 788.19 volt ampere reactive divided by the frequency. In this case, the frequency needs to be expressed in radians over second. So the frequency, according to the data of the problem, is 60 hertz. Okay. So the frequency in hertz is 60, and we need to multiply this by 2 pi to convert this frequency into radians over second, and we need to square the value of the voltage. Okay, and in this case, you need to consider that the voltage needs to be expressed in RMS. And well, the value of the capacitor should be equal to 0.1305 millifarads. Okay. So this is the way in which you can solve this type of problems. Okay. So that is why, well, in this case, the reactive power of this capacitor is equal to the reactive power of the original circuit, because we want to reduce that reactive power to 0, okay? In other words, we want to improve the power factor to 1, okay? That is the main idea. That's why this reactive power is the same as the reactive power of that we originally have, okay? And well, the capacitor that you need to connect is based on this formula. Okay, so that is one approach, well, one exercise. And so I will make another exercise. In this case, we have, again, a voltage source. Let me draw this. We have a voltage source that has a value 120 with 0 degrees, volts RMS. And here is the important factor. First, we have a load. We have a load number 1 that, according to the problem, we know that this load has a reactive power of 60 kilobars, okay? And also we know that this load is consuming a power factor of 0.85. And we know that the power factor is lagging, okay? So we have one load there. Now we have a second load that has the following information. We know that this second load is consuming an average power of 90 kilowatts, and the reactive power is equal to 50 kilobars, okay? And we know that that the power factor in this case is leading. Okay, so that is another problem. And also we have another value that is C. No, we have another dead load, and we know that the power consumed by this dead load is 100 kilowatts, and that the power factor is equal to 1. In this case, since the power factor is equal to 1, we know that the reactive power for this load is 0, okay, because the power factor is 1. So these are kilowatts, okay? So the problem is asking us to compute um, the power factor of the three loads, no, of the combined loads. Okay, also we need to compute the equivalent impedance, okay, of the whole circuit. Now, what is the impedance? The equivalent impedance of the parallel of these three loads, okay? And also we need to know what is the current that is, well, that is demand for from the power supply, okay? So we need to also know this current that is demand, no, by the power from the power supply from each of the loads. And okay, so the idea is the following. First, we can compute the power factor. ¿Qué pasó? Cierra la puerta. So first, we can compute the complex power of the first load. No, let's compute the complex power of the first load. So according to the data that we have, um, we know that we have 60 kilobars. And also we know that the power factor is lagging. That means that this first complex power is in the first quadrant because it is lagging. And also we know that Q is equal to 60 kilobars. Okay. Also, we can know what is the angle, okay, of this complex power if we compute the inverse cosine of 0.85. Okay, this is the angle of this complex power, but we don't know what is the real power, okay? But you can use trigonometry to know what is the real power, because we know that the tangent of theta 1 is equal to the opposite side, that in this case is the 60 kilobars, divided by the adjacent side, that is the real power. So if I solve this equation for the real power, we know that the real power is equal to 60 kilobars divided by the tangent of theta 1. Well, theta 1 is inverse cosine, okay, of 0.85. And this is equal to, um, let me a moment. I need to search for that answer. So the real power is 96.80, 814 kilowatts. Okay, so this is the real power. You can use trigonometry to compute this, the value of this adjacent side of this triangle. And with that information, what else we can compute? Mm, well, we can now define the complex power, no? So we know that the real power is 96.8014 plus, I will place a positive sign because the complex power is in the first quadrant, that is 60. And this is the imaginary part. And remember that we have here kilowatts and kilobars. So we can express the complex power as kilovolt ampere. Okay? I am using kilos here because we have kilobars and kilowatts. Okay? So this is the first complex power. Okay? The second complex power is a little bit more simple. We know that the real power is 90 kilowatts. And the reactive power is 50 kilowatts. Okay? And we can say that these are kilovolt ampere because we have kilowatts and kilobars. And I am just, well, there is an error here. Here you need to be careful because they are telling us that the power factor is leaving. So according to this data, we know that the complex power, no, this second complex power should be in the second quadrant. So the reactive power should be negative, okay? Because it is leaving according to, well, the power factor is leaving. So that means that you're in the fourth quadrant of the complex plane. So you need to place here a negative sign to consider the negative reactive power of this load. That means that you are connecting there a capacitor. No? That's why you have this negative reactive power. So the complex power for this second load is this one. And for the their load, okay, no, this their load, we know that the reactive power is zero. And also we know the real power. So the real power is 100 kilowatts plus J times zero, no? And these are kilobars, okay? Um, well, and this is the complex power for the their load because we know the real power, and also we know them that the reactive power is zero because the power factor is equal to one. Okay. So this is their complex power. Now, the first question was to compute the power factor of the equivalent of the three loads, no? So what we can do is to add together, okay, each of the powers, no? We can add together the power of this load, the power of this load, and the power of this load. In fact, if we add together these three these three complex powers, you will obtain the complex power of the source because the power is divided between the power that the voltage source can provide is distributed between each of the loads, okay? So if we add together the complex power of this first load, the complex power of the second load, and the complex power of the third load, you will obtain the complex power that is provided by the source. Okay, so we can say that the complex power provided by the source is equal to S1 plus S2 plus S3. And if you add together all of these quantities, you will see that the complex power, no, or the equivalent complex power is 286.814 plus 10J kilovolt ampere reactor. And well, I think that's it. Okay, now I can express this in polar form. Okay, and well, if I express this in polar form, I will get the following. And you will get 296.98828 with an angle of 1.9968 kilovolt ampere. Okay. Now, if I compute the cosine, okay, I can compute the power factor if I compute the cosine of 1.1968 degrees. Okay. So if you compute that, you will notice that the power factor is 0.1999. Okay. So this is the, uh, well, this is the power factor. And well, this is the power factor of the combined three loads. Okay. Now, how can we compute the current. Okay, so we know that the power source is providing this complex power. Okay, so we can say that the complex power of the source, okay, the complex power of the source is equal to the voltage of the source, 120 with an angle of 0 degrees, volts RMS, times the conjugate of the RMS current. Okay, so we can know what is the current that the source is providing if we consider the complex power of the source. Okay, and we can use this relationship to substitute the complex power of the source. We know the voltage of the source and we can compute the current of the source. Now, in this case, well, we first need to compute the conjugate of the current. So the conjugate of the current is equal to um, divided, well, I am taking here the complex power and I can divide the complex power by the voltage in order to compute the conjugate of the current. So here we have 120 with an angle of 0 degrees volts RMS. And if you perform this operation, you will obtain that the RMS current, well, the conjugate of the RMS current is 2.39 15 with an angle of minus 1.9968 degrees kilo amperes RMS. Okay. And well, if I compute, if I remove the conjugate of the current, well, only need to change the sign of the angle. So you will obtain 2.3915 with an angle of 1.9968 degrees kilo amperes RMS. Okay. And the equivalent impedance, okay, can be computed as follows, no? Because we can take the RMS voltage, no? We can take the RMS voltage and divide it by the RMS current. So we can take the values that we have. We have 120 with an angle of 0 degrees volts RMS and divide that by the current, that is 2.3915 with an angle of minus 1.9968 degrees kilo amperes RMS, and this is equal to 0.05014 plus 0.001748 J ohms. And this is the result of the whole exercise, no? So just take into account that the power of the complex power provided by the source is divided between each of the loads. So if I know the complex power of each load, I can add them together. And when I add them together, I am basically computing the power that is delivered by the source. And this is the complex power delivered by the source. I can use this complex power to compute the current because I know the voltage by using the definition of complex power. With this, I can compute the current and I can compute the equivalent impedance, okay, if I only take the voltage and divide that by the current, okay? And that's it.